the American Petroleum Institute and Howell Training present An Introduction to Fluid Catalytic Cracking. Crude oil. It starts out here in the ground, formed by organic materials that have been compressed under the Earth's surface for millions of years, and ends up here, powering cars, trucks, ships, and airplanes. And here, heating houses, churches, schools, and office buildings. And even here, in clothes, solvents, plastics, and chemicals. But to get to all of these places, the crude must first be pumped, piped, processed, and refined. This program is about one of the processes, catalytic cracking, that changes oil into products we can use. To understand and appreciate the catalytic cracking process, you need to know how crude oil is structured. Crude oil is made up of hydrogen and carbon atoms that have bonded together to form molecules called hydrocarbons. The hydrocarbons found in crude come in a variety of shapes and sizes. They range from small, simple compounds to large, complex molecules. Different types of hydrocarbons have different characteristics. Small or light hydrocarbons, like methane and propane, are easy to ignite, so they make good fuels. Heavy hydrocarbons, like dodecaine, are thick or viscous, which makes them ideal lubricating oils. The goal in most refinery operations is to maximize the production of light hydrocarbons because they can be used in products like gasoline and petrochemical feedstocks that sell for the highest prices. Catalytic cracking helps us to meet this goal by converting heavy hydrocarbons into smaller, more useful molecules. The cracking of hydrocarbons is accomplished by a chemical reaction that uses heat, moderate pressure, and a catalyst to break down the molecules. The catalyst is a substance that promotes the cracking of oil. When the reaction is complete, the catalyst comes out just like it went in, except for some hydrocarbons and coke that are deposited on its surface. The catalyst can then be cleaned and reused. Heat is an essential part of the process. It is the source of energy that keeps the cracking reaction going. Temperature in the cat cracking vessel is usually in the area of 900 degrees Fahrenheit. A cat cracking unit consists of three major sections, or parts. These are the reactor, the regenerator, and the fractionator. Let's take a step-by-step look at how the whole process works. The cat cracker feed is usually a heavy gas oil or a vacuum gas oil. Normally, the first step in processing is to preheat the feed in a furnace or a series of heat exchangers. Next, the feed is mixed with hot catalyst in a line called a riser. The heat from the catalyst vaporizes the oil as it enters the riser, and cracking begins as soon as the catalyst makes contact with the oil vapors. The oil vapors fluidize the catalyst, allowing the mixture to flow up the riser into the reactor. By this time, most of the desired cracking reactions have already occurred, so the catalyst and oil vapors are usually separated as soon as they enter the reactor. Sometimes, however, the separation is purposely delayed so that further cracking will occur. The catalyst is separated from the oil vapors by passing the mixture through cyclones located inside the reactor. As the oil vapors and catalyst swirl through the cyclones, catalyst particles are deposited on the cyclone walls. These particles slide down to the bottom of the reactor, while the cracked oil vapors flow out the top and are sent to a fractionating tower. In the fractionating tower, the hydrocarbons are separated by their respective boiling points into products such as gas, gasoline, naphtha, light and heavy cycle oils, and slurry oil. This separation process is known as distillation. The bottom product, or slurry oil, contains catalyst particles that are carried over from the reactor. This stream is sent to a slurry settler, where the catalyst settles out. Catalyst and oil from the bottom of the settler are then mixed with fresh feed and recycled back through the system. This is called a slurry recycle. Let's return to the reactor. We said that hydrocarbons and coke are deposited on the catalyst during the cracking reaction. These deposits deactivate the catalyst, so they must be removed before the catalyst is reused. Two different methods are used to clean or regenerate the catalyst. The first step in regeneration is to pass the spent catalyst through a steam stripper. The steam removes hydrocarbons from the surface of the catalyst by vaporizing them. The vapors are then channeled back to the reactor. Next, the catalyst flows into the regenerator. Combustion air is intentionally added to this vessel to burn the coke off the catalyst. The burning of coke produces a flue gas and also releases a great deal of heat. Before leaving the regenerator, the gases pass through another set of cyclones to separate out any catalyst particles that are carried with them. From the regenerator, the flue gas may be sent to a CO boiler. The CO boiler burns carbon monoxide in the flue gas into relatively harmless carbon dioxide. Sometimes the flue gas is passed through an electrostatic precipitator to recover small particles of catalyst. The catalyst particles are given an electrical charge, which causes them to collect on magnetic plates inside the precipitator. Back in the regenerator, the catalyst is ready for reuse after the coke has been burned off it. The regenerated catalyst is mixed with fresh feed, and the same basic process repeats itself. Much of the energy that is needed to continue the reaction is provided by the catalyst, which has absorbed heat during the regeneration stage. You can see that the catalyst circulates continuously throughout the system, from the riser, up to the reactor, across to the regenerator, then back to the riser. The catalyst flows in a cycle from one part of the system to the next. Let's review how the cracking process works and consider in more detail some of the factors that affect this process. Stop the tape and turn to Workbook Period 1. First part of the program, we looked at the various components that make up the cat cracking unit and considered the function of each of these components in relation to the total process. In this section, we'll discuss the operating conditions or variables that affect cat cracker yields and look at how these factors are controlled. You already learned that the goal in cat cracking is to convert heavy hydrocarbons into lighter, more useful molecules. To determine how much cracking occurs in a unit, we use a measure called conversion. Conversion tells us what percent of the feed has been cracked into material that boils below 430 degrees Fahrenheit. The boiling temperature of the cat cracker feed ranges from around 600 degrees Fahrenheit to 1,000 degrees Fahrenheit. So cat cracker products that boil below 430 degrees Fahrenheit must be composed of hydrocarbons that have been broken down from larger molecules. Conversion is normally calculated by measuring the yield of products that boil above 430 degrees Fahrenheit and then subtracting this figure from 100. In this example, 40% of the cat cracking products boil above 430 degrees Fahrenheit. So the percent conversion is 100 minus 40, or 60%. There are a number of factors or variables that affect conversion in the catalytic cracking process. One important factor is the type of catalyst that's used. Different catalysts produce a different range of products. Some catalysts maximize the production of high-octane gasoline. Others increase the yield of jet fuel. The term catalyst selectivity is used to describe the product distribution that can be realized from a given catalyst. The ability of the catalyst to actually convert the feed into lighter products is called the catalyst activity. The more active the catalyst, the higher the rate of conversion. High regenerator temperatures or contaminants in the feed can gradually reduce the catalyst activity and selectivity. Fresh catalyst is added as needed to maintain the desired activity and selectivity, and also to make up for catalyst losses in the flue gas and fractionator bottoms. Another important operating variable is the catalyst circulation rate. Catalyst circulation can be measured by two different methods. The first is called weight per hourly space velocity. The space velocity is determined by dividing the pounds per hour of feed charged to the unit by the total pounds of catalyst holed up in the reactor. The space velocity is usually changed by adjusting the catalyst level or hold up in the reactor. When the catalyst inventory in the reactor is increased, there is a corresponding increase in conversion. This, however, may not be desirable because increasing the contact time between the oil and the catalyst often leads to overcracking. When the oil is overcracked, less gasoline is produced in return for higher gas and coke yields. The majority of cat cracking units in operation today are pure riser crackers. In these units, a bed of catalyst is not maintained in the reactor, so space velocity, or holdup, is not a relevant factor. Instead, the catalyst circulation is determined by measuring the catalyst-to-oil ratio. The catalyst-to-oil ratio is simply the catalyst rate divided by the feed rate. As more catalyst is circulated through the system, the catalyst-to-oil ratio increases. You can see from the graph that conversion increases as the catalyst-to-oil ratio rises. A third operating variable is the reactor temperature. The temperature in the reactor is controlled by adjusting the feed temperature, by changing the amount of bottom product recycled, or by changing the catalyst circulation rate. This chart shows the relationship between reactor temperature and conversion. Generally, high reactor temperatures are desirable because they increase the gasoline yield and octane number. A fourth operating variable is the regenerator temperature. The regenerator temperature is a function of several other variables, such as the amount of coke on the spent catalyst, the degree to which carbon monoxide is combusted to carbon dioxide, the catalyst circulation rate through the regenerator, and the amount of air supplied by the air blower. High regenerator temperatures are often maintained because they reduce the amount of coke on the regenerated catalyst. The high regenerator temperatures also increase the amount of heat that the catalyst absorbs, so less catalyst can be circulated to meet the process heat requirements. The amount of coke that remains on the regenerated catalyst is also considered an operating variable. This is because coke deactivates the catalyst. Conversion decreases as the amount of coke on the regenerated catalyst increases. Another variable that affects yields is the amount of bottom product that is returned to the reactor from the fractionator. This variable is called the recycle rate. Increasing the amount of recycle results in higher conversion and greater yields of gasoline and coke. In most operations, however, a low recycle rate is used because of the problems caused by the coke. The feed preheat temperature is also a factor that affects the unit operation. Raising the feed temperature means that less heat is needed from the catalyst, so the catalyst circulation rate can be reduced. This reduces the coke yield and increases the unit's capacity to process feed. The maximum feed preheat temperature is normally around 800 degrees Fahrenheit. Temperatures higher than this will cause thermal cracking inside the heater. The air to the regenerator is another operating variable. The burning air rate is set by the amount of coke produced. Enough air must be added to the regenerator to burn the coke off the catalyst. But if too much air is added, excessive burning will cause high regenerator temperatures. Pressure in the reactor and the regenerator must be controlled to maintain the proper catalyst circulation. These variables, however, have little effect on product yields, so they are normally not adjusted to influence conversion. The composition of the feed affects what types of products a particular unit will produce. This is because different types of hydrocarbons crack in different ways. By carefully analyzing the feed, we are able to predict the product yields. Most variables in the cat cracking process are measured, recorded, and controlled with automatic instruments. This allows an operator to monitor and adjust the process from a central control room. Let's take a look at a simple example of how this instrumentation works. Suppose the variable we are controlling is the reactor temperature. A measuring instrument, like this thermocouple, is used to sense the temperature inside the reactor. This measurement information on reactor temperature is then sent to a device called a controller that is located in the control room. The controller is programmed to keep the reactor temperature at a desired value called set point. If the temperature has deviated from set point, the controller sends a signal to a valve on the regenerated catalyst line, telling it either to open or close. This changes the amount of hot catalyst entering the riser and brings the reactor temperature back to set point. During normal operations, the instrumentation automatically adjusts the process variables to keep the unit running smoothly. If it is necessary to change the condition of a process variable, an operator can adjust the set point value at the control board. Let's review the operating variables in the cat cracking process and take a closer look at how the system is controlled. Stop the tape and turn to Workbook Period 2. In the normal operation of a catalytic cracking unit, an operator makes minor adjustments to the process to keep the conversion rates at the desired value. These adjustments are for the most part routine, so when the unit is operating normally, it is fairly easy to control. An operator is faced with a greater challenge when the unit is operating abnormally. There may be several different reasons for abnormal operations, so an operator must develop troubleshooting skills to identify and solve these types of problems. In this part of the program, we'll take a look at what causes some of these abnormal operating situations and how they affect the system. In the workbook period, we'll talk about the corrective actions that should be taken for each of these problems. The feed is usually preheated in a furnace or heat exchanger so that it will thoroughly vaporize when it's mixed with the catalyst. There are a number of problems that can cause a reduction or loss of the feed preheat. These include a failure in the instrumentation system, a cutoff of the fuel or steam supply, ruptured or foul tubes in the furnace or heat exchanger, and water in the feed. When the feed preheat is reduced or lost, there may not be enough heat to vaporize the oil in the riser. If this occurs, a mixture of liquid hydrocarbon and catalyst may muddy up the riser and force the unit to be shut down and cleaned out. Another abnormal situation is afterburning in the regenerator. Air is added to the regenerator to burn coke off the catalyst, but if too much air is available, the flue gas may also combust. This uncontrolled burning of flue gas is called afterburning. The primary symptoms of afterburning are a sudden increase in regenerator temperature and pressure. These high temperatures can damage the catalyst, the cyclones, and other metal hardware inside the regenerator. A feed or charge pump is responsible for moving oil into the unit. A loss of power or a mechanical problem may cause this pump to fail. If the feed pump fails, the flow of oil to the unit will stop, and without oil vapors flowing up the riser, the catalyst will not be able to circulate properly. As a result, the reactor temperature, pressure, and catalyst level will rapidly decrease. Obviously, normal operation of the unit cannot continue without a source of feed. An air blower provides combustion air to the regenerator. A failure of this component may be caused by a mechanical problem or a loss of steam or electrical power. If the air blower fails, it will not be possible to burn carbon off the catalyst, so there will be a sudden decrease in the regenerator temperature and pressure. This will reduce the differential pressure across the regenerated catalyst valve. Since the oil cannot be cracked with a spent catalyst, the unit will have to be shut down unless the situation is corrected. Another condition that will cause the unit to operate abnormally is a failure of one of the valves that control the flow of flue gas, spent catalyst, or regenerated catalyst. A valve failure can result from problems in the instrumentation system, such as a controller malfunction or a loss of hydraulic fluid pressure, or the valve may fail because of mechanical problems within the valve itself. The flue gas valve controls the regenerator pressure by regulating the flow of flue gas out of this vessel. If this valve fails, the regenerator pressure may change suddenly. This could result in a loss of differential pressure across the regenerated catalyst valve or the spent catalyst valve and lead to a flow reversal. An equally serious situation will occur if either the spent catalyst valve or the regenerated catalyst valve fails. A failure in one of these valves throws the whole system out of balance. The problem must be immediately corrected to prevent a major upset and possible flow reversal. Gases in the fractionator and the reactor are removed by a gas compressor. A loss of power or a mechanical problem can cause the compressor to lose some or all of its capacity to compress gases. If this happens, there will be a sudden increase in fractionator and reactor pressures. This interferes with fractionating efficiency and limits the amount of feed that can be processed through the cat cracker. It also changes the differential pressure that exists across the spent and regenerated catalyst valves. Another situation that will cause a major upset is a loss of power. A power loss is usually due to problems outside an operator's control, such as an accident, lightning, or a short at a junction box. In the event of a power failure, electrically driven pumps, compressors, instruments, and valves will fail. Unless a backup power system is available, a loss of power means that the unit must be shut down. Problems in the fractionator can also cause a cat-cracking unit to operate abnormally. For example, if a fractionator becomes flooded with liquid hydrocarbons, there will be pressure surges inside this vessel. These pressure surges will back up into the reactor and cause it to operate erratically. Sometimes the outlets at the bottom of a fractionator will become plugged with coke deposits. If this happens, product cannot be drawn from the tower, so the unit must be shut down and the deposits cleaned out. Let's review the causes and effects of abnormal operating problems and consider the corrective actions that should be taken for each of these situations. Stop the tape and turn to Workbook Period 3. You learned that the purpose of catalytic cracking is to convert heavy hydrocarbons into smaller, more useful molecules. We showed you the hardware that is used to do this job. and discussed how each piece of equipment works. Then we introduced you to the major operating variables in the cat cracking process and talked about how these operating conditions affect product yields and conversion. Finally, we looked at a number of abnormal operating situations, such as an air blower failure or a loss of the feed preheat, and discussed the symptoms and solutions for each of these problems. This concludes our program on catalytic cracking. Work through the review and self-test at the end of your workbook. It will help you remember the main points of the program.